And recording. Hey, hello there, and welcome back for more Advent of Code. So, this video is about puzzle 17 of Advent of Code, but it won't be about solving it, because as you can see, it's already solved. And yeah, I did it earlier today, but I somehow screwed up the recording of the video. Apparently, I touched the stop recording shortcut, which is like meta key and R, and I stopped the recording after reading the instructions, and then I solved the thing. But the recording is lost because there was never a recording. So I guess I have to pay more attention to the little red dot here in the OBS icon, which tells me that I'm recording. And yeah, it's a pity because this was a very nice puzzle, clumsy crucibles. It was a pathfinding algorithm puzzle, finally, the first one of Advent of Code 2023. And it was a really interesting pathfinding problem with interesting rules. Basically, you have to move in this grid, which represents a city, and you're carrying on crucibles that are top heavy, and so you have to turn them around, and you cannot go in a straight line for much time. And well, part 2 basically is doing the same thing, but the rules change a little bit. But well, in this video, I left some things left to do on the previous sitting because I had to do something else. And in this video, I wanted to revisit those things. So let's jump into the code. Oh, maybe that's what I did. Yeah, I have this shortcut to open a terminal, which is meta T, and T is right beside R in the keyboard. So maybe I just try to open the terminal, and there I stopped the recording. I didn't notice that, and well, probably I'll have to be more careful with that. So okay, let's open the codes, and this is on the side because I did the usual thumbnail. It takes a long time to respond because, I don't know, when it's starting up, it takes some time to index or something. So okay, this is the solution, and there are a couple of things that I would like to improve, and this is the video for it. Basically, this is the part 1 solution, and it's a call to a Dijkstra's algorithm, and this is part 2. Is very similar, another call to Dijkstra's, but with some things changed in the internal logic. So okay, let's me at least go do an overview of what we did, or maybe maybe I'll just explain what I would like to revisit, and then as we go along, I can explain things if need be. So the first thing that really jumps to my mind is that I basically copy-pasted the part 1 solution and the part 2 solution, and I just tweaked the things that needed to change, and that's it. I then got the answer, and I wanted to end up to finish that session. So that's basically the first thing that I would like to revisit. Let's take note of what we'd like to do. Let's say to do, and try part 1 and 2. Dry stands for don't repeat yourself. So that would be one thing. Another thing that I would like to see if it makes sense to do in another way is reconsider using this enum direction, which we can have, well, the 4 directions up, right, down, left, and also none, because we start not pointing anywhere. So I model this with this instead of using like an option of these 4. And directions can have an opposite thing. And this is basically used in the main Dijkstra algorithm. So the first part of the solution is just parsing the input as usual. We have a width and height and a grid, which I call city, because this is supposed to represent a city where each number is a city block. I have a start. Let's put the start in the beginning. A start node. So these nodes are basically what the Dijkstra's algorithm works on. And the Dijkstra's algorithm, I used it. I imported an external crate for this. In previous years, like 2022 and 2021, I implemented my own Dijkstra thingy, which maybe I can show you if we go to Advent of Code, 2022, and open this code. And I had it already open because, of course, I was revisiting this for the solution. I have this Dijkstra module here, which defines a shortest path function that takes a couple of things. The start, which is going to be a node, an isGoal predicate function that is a function that takes a node and returns a Boolean, and a successors function, which is the most important thing, which is, well, as you can see, ft is a function that takes a node or a reference to a node and returns an it, which is an into iterator, that is like something that can be iterable. Of just these t's. This is interesting because in this year, like 2022, I didn't have any problem that required like different weights while traversing a graph. So I just assumed that all the weights were 1, and that simplified this code, which is not that much. Like this is like just textbook implementation of Dijkstra's algorithm. So, well, that's what I did in previous years, and I think in 2021 I also did something like this, and I just copied it to 2022. But for this year, I wanted to like change things around a little bit, and maybe like I'm not so interested in using like vanilla Rust and without dependencies. So I just added a dependency. You can see in cargo tunnel there's now pathfinding crate, which defines a bunch of different pathfinding algorithms, among them Dijkstra. And well, my previous year's Dijkstra algorithm was heavily inspired, not to say like completely stolen from this crate. And as you can see, this thing takes basically the same kind of functions that my Dijkstra's algorithm take, because I got like inspired by this. I stole this idea. A start node, a successors function, and well, the success predicate. So basically, this is what we are passing here: the start node, the success function. Well, I call it goal, and this basically checks. So let's open a sample file for this. Say 17 sample. There's a couple of interesting samples here, but this is one. You start at the top left and you want to go to the bottom right, and you have to find a minimum path, basically. But there are some rules, like you cannot turn at you cannot go in straight lines for too long. Like you can only go in a straight line for 3 different blocks, and then you have to turn, because it's like these things that you are carrying around, they are top heavy and they want to turn, so you have to like turn with them. That's an interesting bit of the story, and that is basically the rule for part 1, that you cannot go in a straight line more than 3 consecutive turns or consecutive blocks, and you cannot turn around 180 degrees to like turn around, go one back, and then turn around and keep going, like sort of in a straight line with, going back 1, advancing 3, and so on. So that basically is implemented. All of this closure here is the successors function, and this is basically the thing that defines the graph that the Dijkstra's algorithm works on. By the way, I don't know if I mentioned it. The Dijkstra's algorithm is an algorithm to get the minimum path from one point to another. in a connected graph. So this thing starts from a given node, and the nodes, basically the type of the node, you define what they are. They could be just a position, like X and Y position. I want to get rid of these things, of this usize declaration here, but let's keep it. Like this is an XY position. But these nodes, like for my case, I also need them to have a direction, because basically it's important here, this description, it's important which direction you are coming from, because as you can see, like here it did it went 3 times to the right on a row, but it couldn't go to here, to these 3, because that would be going 4 tiles straight in a row, so it turned. And so for any given node, you have to know which direction you're coming to know which are your successors. Your successors is basically your neighbors. What are the next things that the Dijkstra algorithm can visit, basically. So, for example, here, the next ones could be this one, and this one, because you can turn left or right, or you can keep going forwards, because, well, you can still do it here, because you only went 2 times forwards. But the successors of these are only this one and this one, because you cannot keep going forward. So basically that's what I put on my notes for this graph. The XY coordinate, the direction that you're going, and how long have you been traveling on a straight line. And the initial node is 0, 0, because we start at the top left. We have no direction, because basically when we start, you don't have a direction. You can start going right or down, so you don't have a specific direction at the beginning. And 0 is basically, we have been traveling for 0 tiles on a straight line. And then the successors function like takes a node and gives you like what are the next nodes that you can traverse from here. And here I do the usual like 4 neighbors directions. The 4 neighbors that you have in each direction. So it will be and basically I put the XY coordinate and what direction they go, and then I filter these things. And I filter first by checking if they are in bounds. So this get accesses here on the city. I'm short-circuiting these things, so if they are out of bounds, we don't consider this neighbor. So that takes care of, when you're in the border of the city, it's like, okay, here I'm including the up position, and I'm wrapping around to avoid underflows as usual. And then I filter them out with this checked access. And then here there is the different conditions of the problem, basically. If the direction, like if the neighbor direction, this is these things here, right, down, left, up, is equal to, like, is the opposite direction that we are coming from, we discard this because that's basically turning 180 degrees, and so we don't want to do that. We just discard it. We could have used this, or we could have done this in a very different way, like delegating to the direction. It's like, okay, direction, give me your your free, neighboring directions, let's say. So it will be, give me your left, your forwards, and your right, and we could delegate this to our current direction. But I thought that this was much simpler to understand. It's like, okay, we start with the 4 neighbors, and we just filter out the ones that we cannot go. So we filter out the ones that are out of bounds, the one that is opposite, and also then here's the rule of not going more than 3 turns in a straight line. So basically we ask if the neighbor direction is our own direction, that is keep going forwards. We add 1 to this, the 4th element in our nodes tuple, which is, I call it straight length. Like this is the length that you have been going in a straight line. So we add 1 to that if we want to continue in the same direction. Otherwise we start, it means that we are turning around to the left or to the right, so we start at 1 again. And here's the condition. Basically, if it is equal or more than 4, I guess the greater than is unnecessary here, but okay, let's say if it's already 4, then we don't consider this neighbor, so we cannot keep going straight in the same direction. And otherwise, if you haven't early returns from any one of these, we consider this a neighbor. So we have the neighbor x, neighbor y, and neighbor direction, and also how much you have been going in a straight line, and then also the cost of moving to this neighbor, which in this case are these numbers on the city, which represent like heat loss, basically for the exercise. And that's it. That's all of the. Oh, and the third parameter here is basically when we have reached our goal, and this thing takes a node, and we only care about xy position, and if the xy position are equal to our goal, we have reached it, and that's it. This is part 1, basically. And then part 2, what this is about, is the same idea, but the crucibles are like heavier, or they are like ultra crucibles. And so they can keep going on a straight line further, like up to 10 tiles. Oh man, my cat is it's like running races with herself, I guess. Sometimes she's very energetic at night. But yeah, part 2 basically is same idea, but you can go up to 10 tiles in a straight line, but you cannot go less than 4 tiles on a straight line. So this basically are, I don't know, crucibles that are too heavy, and so you cannot turn them around too often. So they have to keep going on a straight. Once you turn, like, you have to keep going on a straight line for at least 4 tiles. So this is the condition that checks don't go more than 10, and here is the condition that checks go at least 4. So basically is, well, if the direction is different than the starting direction, so it's not none, this is also not very pretty, but it works. And the direction is not our current direction, so that means we are considering turning to the left or to the right. Then we also need, and you haven't gone in a straight line like for at least 4 tiles, then we don't consider this. Like, these turns are impossible. Basically, that encodes all the logic for part 2. So as you can see, it's pretty similar to part 1, and that's why I want to try them up. And the last bit that implements the part 2 is also in the goal. We also have to take note of, check how much we have gone in a straight line, because this condition of not being able to turn unless you have gone 4 tiles in a row on a straight path, you cannot stop either. So you cannot reach the goal, like turn and just reach to the goal. And so we also have to check that the straight length here on the goal is also, like, in this case, greater or equal to 4. And yeah, that's basically the whole solution. So the other thing that I want to do, apart from trying this up, would be to evaluate, like, try out not having a direction enum, and instead of this, maybe like having a vector for a direction, and see if that simplifies the code. Consider removing their enum. And yeah, those are the 2 things, like, regarding the code structure, I guess. One other thing that I could try to do that would be fun is also, like, add a visualization for the maze or for the path. Let's say it's not actually add, it's bring back, because I actually coded this while implementing the solution. In order to debug it, I was also printing the city grid to the terminal and drawing the path with a color to see like where the crucible was going around. I think it would be nice to bring that back and put it under like an environment variable to like not always print it, but if you pass an environment variable, print it. I think that would be a fine idea. And then the last thing is that this is taking a little bit long to run. So if we run this with the actual input and build it in release mode and then time how much it takes to run, this is taking like more than half a second to run, which is a bit on the higher end of what I would like. So I would like to optimize this with some very like high level optimization, no low level things. Maybe with an A* algorithm instead of Dijkstra, or by parallelizing part 1 and part 2, basically, because now, like, if both parts are taking a significant part of that half a second, running them both in parallel should make things faster and should be pretty easy. So let's start from the beginning, I guess, trying up or extracting something to have part 1 and part 2 like do basically the same thing. Tonight I'm drinking red tea instead of mate. So basically I'm going to copy part 2 solution, part 2 solution, because this actually has the two conditions of a higher, basically part 1 and part 2 are the same thing. You can think of them in the same way. Like part 2 has a minimum distance that you have to go in a straight line before turning, which is 4, and a maximum distance also that you can go with, which is 10. And part 1 also has a maximum, which is 4 in that case, but that doesn't have a minimum. So we can say that the minimum distance is 0 in that, and then implement both with the same code. So let's, I'm just going to grab all of this, copy it from here, and put it under a function that's gonna be finds mean heat loss, because that's what we're doing here. And I don't know what this is going to take, surely the grid, that's for sure, but it's going to return just a number. And I think U32 was the thing that it returned. So this is what it will return. Oh, and this can fail. So what happens if, come on cats. I think this is the only condition where this can fail. Can find. So should I return an optional or a result with this? Well, let's just return, a result for this. Okay, and otherwise we're going to say okay, and let's call it mean heat loss, not part 1 or part 2 here. Okay. The start node, we also need to have it there, and the goal, I guess, should also be there. So let's copy these two things. I'm surely going to receive the grid, so let's copy this. And actually, if I'm going to receive the grid, this probably can be inferred. The grid is called the city. Sure. And width and height is also part of the grid, so this also comes with us. Let's put this here. So okay, it already has everything that it needs. So let's call this thing here for part 2, maybe. say let this be finding heat loss for the city. We're gonna pass it as a reference, though I think it is already a reference. Yeah, and I didn't want to make this a reference. It's actually, yeah, this already is compiling this function, but of course it needs a couple of parameters, which is like the minimum straight line that you can go. So let's just call it min straight line, or straight length, which is like what I'm calling this thing here. What are these things? I32, weird, I guess it's using just the default number type. Let's have a U32, I guess. And max straight length, which is also a U32. Okay. And then we should use them and say, okay, if the straight line, like the minimum, we're going to say, for instance, for part 2, that that it's 4, so that's less than the minimum. If it's less than the minimum and we want to turn, let's say no, we cannot turn. And the other case is that if we want to keep going the same direction and it's above, so yeah, it's more than the maximum, max straight length, then we also say no. And in order to be a valid goal, we're going to say that straight length has to be greater or equal than the minimum straight length. Okay. I guess that's all that we need. For part 2, then, these numbers are 4 and 10. And then I'm just going to remove part 1, assume that this thing will take care of it, and say mean heat loss for part 1 is going to be same idea. Should I say 0 or 1 here? I'm not sure. I'm going to go with 0 because, like, let's see, mean straight length. Yeah, it's never going to be less than 0, so this condition is not going to be met, and this is always going to be greater or equal to 0, so yeah, it seems fine. And the maximum should be 4, I think, for part 1. Yeah, and I guess this thing already returns a result, so we can propagate this thing up. We don't need any of this, I think. And the city can be inferred. That's awesome. That's awesome. Okay. So is this it? Like for the extraction? If we run this thing now, do we get the same? Yeah, no, we did. We screwed up part 1. Yay. That is fun. The straight line, I would like to maybe, let's run the check samples. Okay, the sample, sample A is giving a smaller answer for part 1, and sample B is also giving something smaller for part 1. So where did we go wrong? The maximum was Oh no, it shouldn't be 4. I think it should be 3, because you cannot go more than 3, I think it was, in a straight line. So here, max, where is it used? Yeah, if it's 4 or more, then yeah, they should now pass. Yeah, okay, it was a stupid mistake. And we can check all. This I don't expect to be faster or slower than before. Now, this was not an optimization thing, but we did extract the the general case for the solution, so that's pretty nice. The parsing here is particularly ugly. Like, I don't particularly like the, well, but we have done the first part. Let's remove this first part, and let's actually just commit this. I'm not going to commit the readme because that is just our to-do. So extract common function for part 1 and 2. This is basically on day 17, and that's it. Okay. I was checking the parsing, which I don't particularly appreciate when Rust like leans to the right this way, and you know the nested things don't look too nice. Here we are basically getting each character and checking. Yeah, it's not bad. Unexpected not digits character. This is basically the, maybe we can like extract this little fella. I'm not sure. Even this. This is what like parse digits. Does it meet the? Yeah. I don't know why closures cannot infer the types in situations like this, but maybe something like this is a little bit less unwieldy. Yeah, I prefer this. Okay. That was not part of to do, but let's have this change to commit. Okay. Yeah, the visualization for the path. That's something neat, I think. And oh, I think the error message here, couldn't find the path to the machine parts factory. Yeah, with ultra crucibles is not something that we want. I guess this thing, like the original Dijkstra thing, returns an option instead of a result. But if we want to propagate the results app, it's like we would have to convert that option into a result. So we can just return the result from here, and that's fine. But yeah, this Dijkstra function returns an option that has, well, a tuple of two things. The thing that we are using, which is like the total cost of this path, and the path itself. So with that path, we can draw things to the terminal. I think this looks quite nice. So I'm going to bring it back. So we are basically going to iterate over the city, I think. Let me think for a second what I want to do here. The path itself, it's basically a vector with all of the nodes that we went through. So the nodes have the xy, the direction, and the straight line length. So I guess we are going to do it in a very simple way. I don't remember how to check environment variables. I think there was an env var or something. Oops, I had the thing, but yeah, vars, var.os. What does var do? Fetches the environment variable. Yeah. We return an error. What does it? Oh, a result. Okay, let's just say, give me, I don't know, debug maybe. And if it's okay, and what do I want to do? Like, just if it's okay, I don't care. Yeah, I don't care if what the value is. If you have said this is fine. Inside of here, I'm going to print the city. So let's say that I do just a cargo run of this with the first sample, which is a nice one. And if we do debug 1, yeah, it's going to be printing the city. Okay. So what are we going to do? We're going to go for each row in the city. This is already a reference, I guess, so we don't need to do into iter. Although I will need, I will need the position of this. So let's iter and enumerate. So this will give me the y coordinates and the row. Then for x coordinates and the tile in the city, I guess. City is a city block basically. In row, again, iter and enumerate. Well, let's make a string for each thing and what? And just print it, right? We can probably do something a bit more iterator based. So let's say let s be a string, and it's gonna be this thing enumerate blah blah. Then we're gonna map these things and we're gonna collect into a string, and then we're just gonna print that string. Println s. Beautiful. Even we can say line. Okay. And what are we going to map this each block into? Well, first let's just print the block numbers. So this collect, I think, yeah, in order to make a string, we'll have to print each character, right? Which might not be the best. Well, let's just say, yeah, because if I want to print these things with colors, single characters won't do. That is what I did the last time. So let's just use a for loop. So line is gonna be a new string here. Then we're going to for and iterate with old school way. In here. Okay. And what are we going to do? We are going to, well, the block is just a number, right? Yeah. we're going to convert the block into a string, basically. We can just say it's a string, right? Yeah, not... Yeah, let's do that. 9. No, like this will allocate unnecessarily, but it's just a little thing. Yes, with this, we should just print the... Well, there's no separation between these two. Maybe let's add a final end line here. Print line. Yeah, so this is basically the map, the first sample. Nothing fancy. We can also print the path. So I'm going to use this variable, and here for each x, y, we could ask if the path contains these x, y coordinates. So algorithmically, this is not very pretty, but this is just when you're calling this with a debug environment variable, so I don't care. So we're going to do path. How do we ask if this contains? Well, we have to iterate it and ask if find, let's say. Yeah, we could also ask contains, or but we're going to use this information. So find the node whose xy, and we don't care about anything else. This is, well, and nodes xy, or let's say path x, path y, px, py equal our xy coordinates that we are working on here. Let's say we can say if this is a thing, if let some I don't know, path segment or something. We're gonna do line, let's just push an x here into the line, and otherwise we're gonna do what we were doing before, just to see this is the problem, this is a reference, and this is not a reference. We can, I guess we can do the reference here, right? Now, who is your... Oh, these were like double references, right? Now, what's your... px is a reference to usize, and x is reference. So if we the reference once here, we should have... Do you want to double the reference? Well, sure. Go with that. So if we print now, you can maybe see the path of x's here for part 1 and part 2. But this is not very very easy to see. So adding some color here will make things pop out much nicely. So this is... What do we care about this? We're going to care about the direction, basically, only that. So this is a tuple. We don't care about x, we don't care about y, we care about the direction, and we don't care about the last thing, which was the straight line length. So we're going to have a character, let's say, let's character b and match this direction. Well, the good part about having an enum for directions is this kind of thing. If it's none, I don't know, x is where you start. Oh, well, if it's none, basically this is the start, so we can just say s. If it's up, of course, it's going to be the this symbol, which I never carried, right? If it's right, of course, a greater than sign. If it's down, a v. and if it's left, a less than sign. And finally, I'm going to push this with a little bit of color, but I never remember how to do Rust print color to terminal. And of course, I have this result in violet because there is no chance that I'm going to remember these kind of escape codes. So you want to push something like this, where instead of this error we put the, well, we can push string and format this guy, so extra allocations unnecessarily, but who cares for debugging purposes. Here goes the character. This color is, well, what's your problem here? This probably returns a string and the thing wants to slice, so that's the reference. Oh, it's yellow, but look at that. That's very pretty. You can see the, let's actually use another color. One is red, is 0 green? I don't remember. No, it's a gray thing. Is 2 green? Yeah, but it's not very pretty. I don't remember what these colors, how these colors worked. There is some bold things. Arch wiki terminal. I can see it here. Color output in console. Give me a table of things. Is this not what I want to? Give me escape codes. Come on. Terminal color escape codes. Yes, something like this is surely what I want. 31. Red bold, yes, 31 1 and underline. No, that's too much. But is like 31 what I want? I was running it here, right? Well, red works quite well. This, what is the difference between bold? Bold is like this. No, that's simply something. Oh no, it's a semicolon, not a comma, of course. Ooh, bold. That looks better. Even blue, maybe? No, that's red. Red is the best, I think. That's yellow. That is. Ooh, blue also looks quite nice. What else do we have? Magenta, right? Magenta also looks nice. Even maybe not bold. Huh. That's actually quite pretty. But I mean, a bold blue was quite a contendant, I think. Yeah, that's also nice. But yeah, you can see the difference between the paths between part 1 and part 2. In part 1, it is a bit more wobbly because it has to turn and it cannot go more than 3 times in a row in the same direction. And part 2 is like it needs to stay more directed, it wants to go more in the straight line. I want to run this thing on the other terminal because it has a higher contrast. So let's paste this here. No, I am in the wrong advent of code. Yes, this is what I want to do. Look at that. That's very pretty. And if we run with the other sample, this is a tricky sample. It's to exercise like part 2, but it also is working fine. And can I see the actual input? Because I don't remember if I saw the actual input is giant, massive. But ooh, look at that! It makes like a turn. It's very pretty. And I wonder if like the numbers in the middle, yeah, it looks like the numbers in the middle are higher. There is sort of a pattern that looks like a bulge, at least to my eyes, here. Maybe I'm imagining things, but yeah, I see much more like 2s and 3s and 1s on the edges, and more like higher numbers, 8s and 9s in the center. So I guess that's, you know, so you don't have to, like, you don't cross around in diagonal here. But this is, yeah, this looks really neat. I also like how it probably prefers to go on a straight line on the like more near the top like this, but it has to make these horrible turns. So it's like it does the best it can. Oh, I really like these pathfinding problems where you can like really visualize the solutions. And the example for part 1 is also like a pretty nice pattern, I guess, that exemplifies both parts quite well. This actually does look like a nice thumbnail for this video. I'm going to check thumbnail done. Okay, so and this is the code for printing, which is like, yeah, I think I'm okay with this. Maybe it's a bit ugly to have it here. If I extract it, like, does it need to take many things? It doesn't need to take too many parameters. So maybe it's nice to have it on a separate function. Yeah, let's leave it like relegated to the bottom. So this thing is prints prints path, debug print path. Sure. And let's actually use a is error here and an early return, which is always nice. And otherwise, we are just going to do all of this. So less indentation. City, I probably want to have an alias for this, because I'm using it in a couple of places. So type grid is going to be this, and this is going to take a grid. Sure. And yeah, this code is, it's not too bad. It's not too good either. But yeah, iterating like this linear search inside of two loops is not very pretty. I could convert all the path, I guess, into what? Into like a hash map from coordinates to the direction, which is the only thing that we need. That's, I mean, I don't really care about that here. So that's fine. That is fine for me. Great. Let's commit this as a separate thing. What did I change? Yeah, this thing. Okay. Add debug prints visualization for day 17 path. Yeah, minimum path. Sure, that's what we did, and it was nice. So this is checked. Consider removing the direction enum. Yes, I think that's what I want to follow along with. There was one thing that I was wondering, which is that do we need to specify these useSize types here? Yeah, but for some really weird reason, like in my mind, which is that this is using this wrapping sub here, and even though we are then using this xy to well, converting this, but then we are using this to index the city, which will take a useSize. Like it's not inferring this thing to be a useSize, so it's a bit sad. But well, that is what it is. So we have this direction enum. Let's sketch out what I'm thinking about with more tea. More tea, please. Yeah. So, what I'm thinking about is what if we, instead of doing these things in the nodes, we just say, okay, the differences, you know, let's have these 4 things be the 4 directions written as vectors. So this would be right. This would be left. Like we don't have to go in any particular order, I think. So right, left, down, and 0, -1 is up. So in Twitter again, and now filter map again. This would be dx and dy and no direction. Okay. And in order to get then nx and ny, we would add x wrapping add signed, and we would add dx, and same thing but with y. Sure. Yep. So up to this point would be the same. Now we also need a direction here, but for the direction we would be storing this dx dy, I think. Right? Yes, I think so. Because we wouldn't have the enum again. Oh, and we also have a none, which is like not very nice. But we can get around that. We can get around it. Yeah, I think we also have like the starting position, so that's also checking for this is the same as checking the starting position, so we can sort it out. We can work it out. We can work it out. Yeah. So let's pass an x, like the xy. This would be the position. I am a little bit tempted to wrap this in an extra tuple. Yes. And pass here another tuple for the dx, dy, so the direction. So then each, each node will have one of these. So the starting node will have a pair like this, 0, 0, and also a pair for direction, which I think should also be 0, 0. I hope it can infer it. Here we can maybe call this thing position, where are we using x and y? We are using it here, right? Well, I guess we could extract x and y. All right. How do we say, okay, opposite? This is like the direction of the node that we are evaluating, and then this is the direction of the neighbor. So we cannot do something like this there, like doing that opposite be minus there. This is not a thing, right? Like this is a yeah, this is a tuple. So yeah. Let's say let is opposite. Let's write it down. I want to find a like destructure this and put a better name, but I already have taken dx and dy here, which might not be the best names. But I can only think of worse names. Because if we call this thing, yeah, dx dy, so the other possibility would be calling this thing neighbor dx, which is already like a pretty horrible name. But let's go with it. Let's try it out and see what happens. So instead of direction, we're gonna have dx and dy. So this is the position xy and direction dx dy. Sure. So is opposite would be to check if this neighbor direction x is equal to minus dx, and well, we could say neighbor dx and neighbor dy equal dx dy, right? Where else are we using the direction? I want to see. Yeah, here. You know what? I'm just tempted. Can we say this? And I know that I'm going back and forth a lot, but my OCD will, like, for naming will kill me otherwise. Let's go back to the x dy. And here we're going to say, okay, it's opposite if the direction that we are going is minus dx and minus y. And if this is the case, so if it is the opposite direction, we just early return. Let's actually inline this variable because it doesn't really do much. Remove useless parentheses, yes. Now we want to say, hey, if we are turning, so if the neighbor direction is different than my direction, then we do stuff. Yes. And this thing about asking if it's none, we could ask, yeah, if direction is 0, 0, basically, which is the starting direction. Or even like if xy is the starting position. Actually, we were asking if it's not. So yeah, if it's not 0, 0. So same thing as saying if xy is not the we don't have a starting position, so well, yeah, then let's say if direction is not the starting direction, and the dx dy is different than the direction, so we are turning, we do all of this. Okay, great. Then if it is the same, yeah, we do this. Okay, so far so good. We can also here extract position, direction we don't care about, and just ask, hey, is the position equal to our goal? And the straight length greater or equal than that. That's great. And here, did I do the... oh, this is taking the path. Huh. I didn't realize that we were passing the path by move, which I don't think is the best idea. Like, okay, it makes it leave only what's needed, but here we, oh, well, this is, so far the things have gotten, I think, quite better without the direction enum, but this one, the debug printing, might get a bit worse. So let's comment it right now, and the direction enum can die. So it's really much less code. So the question is, does this still pass all the checks? With some warnings, but it seems like it does. Awesome. So that's great. Now this debug prints might get a bit uglier. So the path will be these tuples of positions and directions, which are going to be eye size, I think. Sure. Beautiful. And then we search for something which we can actually extract here as position. So yeah, we want the path whose position is equal to this thing. All right. So far this is not bad, to be honest. Not bad. We won't have the start. Well, unless we do the path. Yeah, we could still do. We are matching the direction, right? So yeah, this is, let's say, direction. We're gonna match this thing. I don't know if we need to dereference here, but let's actually rewrite all of this and put a little tuple here. So I don't know why I'm not receiving complaints from Rust. I surely have some error, right? Like, how can this not complain? If we run this, 67. Oh yeah, we have problems here. px and py. Oh, I think I screwed up. Oh, yeah, I confused these two things. Sure, and now it's complains rightly so about this thing. So what is up? It's -1. Right is 1 here. Down is 1 here, and left is -1. So let's actually do left, right, like what makes sense to me. Left, right, up and down, down and up, yeah, or up and down, yeah, left, right, up, down. And anything else is like unreachable. We know, otherwise it's a bug. So very complex type used. Consider refactoring into type definitions for further info. Blah, blah. Like, well, what can you do? Like, yeah, I know it's complex, but come on. Really, Clippy? Like, really, are you going to? Really? I bet you if I extract this into a type variable and I call this thing node, yeah, you don't complain anymore. So yeah, you know what? Take that. And now this one is going to be even better. The start is going to be a node, or even here we can say that this parameter is a node. No, can't we say this? It's a reference to a node. Yeah, and I could remove here the underscore usize from starts because, well, now we have a type for this. So thanks Clippy for that thing, and I just defined the type alias, and the type is still as complex as before. Okay. I think that was a successful refactor, like changing the direction to be two things, and still everything passes, right? So no problem with this. Now, and does it take basically the same time to run? I mean, the nodes are a bit bigger, but it actually seems like it's slightly faster. Yeah, look at that. I was not expecting that, but that's awesome. That's great. Like each node is now bigger, but it's not the size that matters, it's how you use it. Oh man, maybe I shouldn't be recording videos at 12 p.m. Okay, or 12 a.m. 00 a.m. basically. So what else was I thinking about? This thing, goalies, these, I guess this is fine as a success function. I was thinking a little bit about like extracting some of this to not have everything so clamped up and nested. So let's see how it looks. If we call this thing, yeah, successors. We're passing the start, the successors, and also this is the, like, I don't remember, success I think it's called, extract into variable. Yes, this is the success function. I want to move this thing up here, I guess, but these instructions didn't really lifetime problems. So what's your problem here? So what type is more general than the other? Right, disclosure does not fulfill the lifetime requirements. It's like this is used here. So the success thing, yeah, this takes a reference. Maybe if I don't, what if I say this is a reference to a node? Would you be happy with this? Would you be happy with this? What? Okay, sometimes the closure, like local variable closures, really like to have the type parameters on their, yeah, types defined on their parameters. So okay, that made it happy. Not really sure why, but sure. If the position of this node is equal to the goal, and our goal is this, which I think I almost want to inline, to be honest. Yeah, we start here, sure. This is a node. This doesn't add anything, but maybe it makes things a bit more readable. The success for the algorithm is getting to the end position and having this straight length requirements. Success source is this complicated function, basically the soul of our implementation, and then we just call Dijkstra with this, and that's great. Yeah, I think this was a pretty nice refactor. You can probably look at the difference. It should be shorter, I think. Yeah, we saved quite some lines because we don't have this superfluous enum. The only bad thing about this refactor is that this thing requires like an unreachable condition, but it's like, meh, it's fine. It's fine. Yeah, the rest of the things I think are pretty fine, I think. Yeah. Let's commit this. Let's add this and commit. What did we do? We remove dir enum and use dxdy tuple instead. Beautiful commit message. That's what we did now. Awesome. And now for the fun part, I guess. Optimization. No, the fun part was printing things to the terminal. Now for the other fun part, which is optimizing things. So we are running this in release mode with the actual input, and it's taking 500 milliseconds or something. I wonder, well, I wonder if using A star, like I was thinking about parallelizing this too, but let's see. I'm more curious about whether using A star would be significantly, like it would make any difference than with Dijkstra. So A star, can we isn't it called like A star? Don't you have an auto import star? Come on, pathfinding. Let me. So director thing. Do you have A star? Yes, you have A star. And what do you have inside here? You have A star. So you just didn't want to import it. That's sad. So A star, because the namespacing on this crate is crazy. Like this is too much. Pathfinding directed A star. I guess like, yeah, this is the module. A star is the module where the A star function lives, and this is a directed pathfinding algorithm. Sure. But it's a bit too much. Like A star, but what does A star take? It also takes a heuristic, and a heuristic is an approximation of the cost from a given node to the goal. The approximation must not be greater than the real cost, or a wrong shortest path may be returned. So yeah, the idea of using A star here instead of Dijkstra is because, well, Dijkstra just follows the graph and sorts the nodes that it visits by their cost, basically. And then whenever it visits a new node, it adds all of its neighbors or its successors to like the unvisited nodes, and then it takes from the unvisited the one that has the less total cost. So it's like minimizing cost. So whenever you find your goal, you know that is the minimum. So it keeps iterating like for the shortest. And we know that these solutions, like the answers to the samples are around 100, but for the actual things, it's like they're not too long, but they probably have explored a lot of things. And when you get turn around quite a lot, it probably has explored a lot of paths that don't make much sense, because you can see that this thing really wants to go to the end. And that's what A star does. You can posit an heuristic function to like say, okay, sort of go in this direction. And in this case, we know in which direction we want to go. We want to go to the right and to the bottom right corner. And none of the numbers here is 0. So, each has at least a cost of 1. So if we just say as a heuristic function the difference in y and the difference in x as an approximation of the cost, I think that can direct our pathfinding, like the pathfinding algorithm. So let's see if that makes sense. So the heuristic is the third parameter. So heuristic, and this thing is the successors at heuristic b. It's going to take a node again. So this is going to be a node, and it will return an approximated, I don't know what that import was, an approximated cost. And from this node, we are just interested in the position, I think. I guess, yeah. So this will be a very conservative estimation, and we are just going to say this position. We can extract it and say xy, and we also have our goal here. Starts. Let's call this thing end, I guess. But well, it's not the same as the start. Let's call it goal. So the success is when the position is our goal. Yeah. And sure. Yes. So we want to say x absolute difference with goal first coordinates plus y absolute difference with the goal y coordinate. Okay, not y, yeah, y coordinate. And this is not a valid heuristic because it's returning U size. Yeah, because we want our cost to be U32. Is there a good reason to use U32? I don't think so. I think we can just return a U size here and this will be happy. Here this cost, oh, because this cost comes from the city, and the city is parsing things as like 2 digits. Okay, let's use U32. So this thing has to be casted SU32. Not very pretty, but fine. Yeah. Okay, now it's compiling at least. I think there's no problem. So first of all, does it check? Does it check? It does. Now it took a little bit to run the answers, but let's time it. And it's not better. So A star is not being better than Dijkstra. It is finding the same answer, but it's not really directing the algorithm too much. I wonder if I did something wrong. I mean, this heuristic, that does make sense to me, but maybe it's not making a lot of difference because it's not a very good approximation, because like most of the nodes are big numbers, so it's a very, very conservative estimate to just say 1. The problem is that if I use a bigger number, I run the risk of overestimating, and then it can give me a wrong result. Yeah, I think so. Okay, so using A star didn't work. It didn't really work, right? So we can just discard these changes. Let's take a look at the changes, but I think we can just discard them. Yeah. Dijkstra for the win. I don't know how the pronunciation is goes. So yeah, let's discard this. Okay. So we have tried A star, it didn't work. Let's try the other thing, which is to parallelize this. But in order to parallelize, we need to know if like part 2 and part 1 are comparable in some way. So let's, yeah, this is taking like 540 milliseconds or around that time. So let's do only part 1 instead. Now that's taking, well, it's not really good for parallelization either, because like part 2 is doing like most of the work. Part 1 seems to be taking 100 milliseconds, and then part 2 is taking like, yeah, 400 milliseconds. So we can shave 100 milliseconds by running these two things in parallel, which, I mean, it's not bad, but it's not great either. And doing something different would require actual thinking. Like probably using my own Dijkstra algorithm to optimize things a bit better, because one of the problems with, now I sort of remember that this crate is trying to be as generic as possible, because of course it's a generic pathfinding crate, and in order to do so it tries to put the least restrictions on the types that you know, your nodes basically. It still puts some restrictions, like it requires them to be implement EQ, hash, and clone, and then it uses some interesting data structures inside to work. But I think in my previous year solutions, I also required those things to be order, to implement order, and you can derive that and make them, you know, have an order, and then you can use the binary heap map, which makes things, I think, makes things quite simpler. So I'm now wondering, does it make sense to use my own Dijkstra? I don't know. And does it make sense to parallelize this? So this thing has results. Yeah. Let's try, to do a rayon. What is what I want? Join? Yeah. Join takes two operations, and the two operations is basically part 1 and part 2. That is what I want to parallelize. So just a thing that does this, and another thing that does that. And this can be mean heat loss part 1 and mean heat loss part 2 can be assigned to a tuple. So can you do that? What's your problem? Cannot be sent between threads. It's not implemented. Yeah, this is not really nice. If I tell you to be this, then you probably won't be happy. Well, let's unwrap for now and run this. Like, this is what we expect, right? Like, it's parallelizing, and we went from 550 or something to 400, like 100 milliseconds less, but it's not significant, to be honest. And do you have some sort of like try join? Like, yeah, okay, these things cannot move between threads, and that's what Rayon needs them to. We can probably make our AOC results not do that. Although this doesn't need to be a result, right? Yeah, this could be an option and just return the option thing that Dijkstra does, and then handle the options here, I guess. That's also a possibility. Yeah, but I don't think that this really makes that much of a difference. So okay, I also not very interested in parallelizing this too, I think. Maybe I will do it off record. So that's kind of a downer for the ending. I was not able to parallelize things. Should I try to implement my own Dijkstra? Like, should I try? Or, I mean, implement not, let's just copy the one that I used in previous years. I mean, it's already an hour and 30 of video. I should say no, but I'm really tempted to say yes. So let's follow our hearts. Let's go to previous years Advent of Code, open this thing, and just copy this Dijkstra thing and paste it on our, like, besides our lib. It's going to be called Dijkstra, sure. And I also want to take inspiration on the 2021 year. So let's go to 2021, open this, because I think for 2022 I was not considering different costs, but for 2021 I did. So let's also paste this here. This is going to be Dijkstra copy. We can call it Dijkstra. Let's call it Dijkstra 1 and Dijkstra 2. Beautiful, like, very good names. And let's close Advent of Code to 2021. This is just to see. Yeah, let's just try to quickly see. So I think the one from 2022, I mean, it could have some improvements on, or no, it doesn't seem to be like very different. Notes, and I'm just looking at it from a high-level glance. The one for 2022 is taking an is-goal as wait, this also takes EQ hash and clone. It's not. It also needs. Oh, it makes this node be. So I don't expect this actually to be faster in any way. Huh. So okay, and this that's the same, right? Seems so. Okay, so let's grab Dijkstra 1, but this cannot take just the end. It's going to take an is goal. Okay, so let's modify that. Is goal, and it's actually going to move it to the bottom, and PT should be this. Yeah, and step is called is success, basically. What we just take all the inspiration from. This is not giving me any errors or anything because I need to include it as a module in here, I think. So if I said mod Dijkstra 1, that's what I want. So yeah, type check these things. PT, what don't you like about this? Oh, it's another type parameter. So sure, something like that. Great. And now you don't have an end. We're just going to call is this success for the value. Okay. So we're gonna pass the value and ask if it is success, and assume that all the rest is okay. This is called Dijkstra 1 shortest path. Sure, let's try this out here. So instead of using this Dijkstra, we're gonna use our own AOC Dijkstra 1 shortest path. Pass these things, and it's not going to return the path. So we can get rid of the path and comment this, and this is returning a use size. So that's because, yeah, the cost can only be a use size. That's not parameterized here. So I guess that's what it's complaining about. That returns blah blah, but it returns, yeah, use size and U32. Sure. So don't worry. We're going to put use size where we care about. So those things should be use size. The thing here, these things on these specs could be use size, or we could transform. Yeah, this cost here is this as use size, basically. And that's it. And Dijkstra 1 module is private. What? Let's go to the lib here and say public mode Dijkstra 1, and then this can use it. Awesome. Okay, so now it should be using our own module. Let's close this. Around Dijkstra algorithm. Let's let it build and run, and it's taking longer. Of course. I thought that we could get it faster, but no, actually that's a good lesson. If you use a crate that implements things, you know, people have taken a lot of care to make those things fast, and it's probably going to be faster than your bespoke solution. So okay, that was also a bummer, but it was an informative thing to do. And yeah, now we know that discard everything. Our custom Dijkstra thing is not better. I mean, the only way that it is better is that it's also fulfilling to try things on your own, and you also have one less dependency, I guess. But other than that, it's not really better. So I think that's it. It was a nice refactoring session, and well, not so nice optimization session. In order to know what's going on, I would have to actually profile this thing and try to think of some better approach of going through this. But yeah, I think for now that's going to be it for day 17. I'm quite happy with the solution and how it looks now. Like having especially like extracting part 1 and part 2 to be like sort of generic and say, okay, these are the conditions for part 1 and the conditions for part 2. I think that was the best refactor. And also being able to run this in with the debug thing. And whoops, what happened? Oh, we are again on the wrong advent of code. But if we go to 2023 and run this is also very pretty, and I like it. So that's it for today, I guess. If you have been, thanks for watching, and see you later. Bye bye.